All right, so we left off speaking about the ionic movement in a pacemaker cell, and let's just sort of recap what we said here. So we started out at rest, right, at negative 70 millivolts in terms of the membrane potential of our pacemaker cell. And then we stimulated a brief period of depolarization by opening up our funny channels, which are mainly sodium channels, and closing our potassium channels, which are always open at rest. So we close those channels, open up some funny channels, and that begins this depolarizing period here. This further triggers, so the presence of that excess calcium in the cell, sodium in the cell, further triggers calcium movement. So we open up here some fast calcium channels, also called T-type or transient calcium channels. And they don't stay open for very long, and they don't give a very meaningful impact in terms of changing the membrane potential, right? But they do lead us to threshold. So the opening of those fast calcium channels here gets us to this negative 55, which is our threshold. And threshold here means the same thing that it does when we study the typical action potential, right? We're now going to rapidly depolarize the cell. And what's responsible for that is the opening up of our slower calcium channels. These are also called L-type calcium channels or long-lasting calcium channels, and they are going to rapidly depolarize the cell by allowing that influx of calcium, okay? And that's the upstroke that we see here, which leads to our action potential. Okay, and then the final phase here is that we sort of flip-flop what's happening in the rapid depolarization period in order to repolarize this pacemaker cell. So we left off describing this final leg of this graph. And what's happening here is that we have a decreased permeability to that calcium because we close those calcium ions, those calcium channels. But we open up our potassium channel. So we increase the membrane permeability to potassium, all right? And what is the ECDF for potassium? What direction is it going to want to go in? Outside the cell, outside the cell. And so that is going to be responsible, just like we saw in that typical action potential in a neuron, that is going to be responsible for the rapid repolarization here. Okay, so here we close our slow calcium channels, and we open potassium channels. Okay, and obviously if we are opening potassium channels, again, remember we close them up here, right? So from rest, we started with them closed, and now we're going to reopen them. And so the membrane potential is going to get back to where it is at rest. It's going to start to approach the equilibrium potential for potassium, and that's going to rapidly repolarize the cell, okay? All right, so this is a pacemaker cell. This is what's happening to generate an action potential here. I do want to point out this action potential is not involved in contraction. So in pacemaker cells, contraction is not the important part here. So we don't have an extended period of time. This is a much shorter time than what we'll see with a contractile cell. And that's simply because pacemaker cells are really just about generating the action potential, generating the rate, generating the rhythm of the heartbeat. And they're going to propagate this action potential onto a neighboring cell, which is a contractile cell, which is going to do the actual contractile machining, or actual contracting, right? Cross-bridge cycling. Okay, let's move on to look at the ionic basis in a contractile cell. Okay, so here we're looking at a contractile cell, and again, we're going to start with our graph, which compares time here and our membrane potential. All right, we start off with our same variable, so negative 55. being our threshold value. And then a contractile cell actually hangs out at a little bit more negative than a neuron or a pacemaker cell. So resting is going to be negative 90 millivolts. Okay, it's a lot more negative. And that is our rest. Okay. And so what we start with is from rest, we then rapidly depolarize. Okay, that's where we fire our action potential straight away. Then we begin to repolarize. And then for a very important reason, we have to interrupt this repolarization period. I'll talk about why, and then we can continue to rapidly repolarize. Okay, so we have 4 phases here, which we'll outline here. So we start at phase 4. Then there's actually a phase 0 before we get to phase 1. So phase 0. Then we have phase 1. Oops. It's phase 1. Then phase 2, which is our plateau or sort of our delay phase. I'll explain what that means in a bit. And then finally, we have phase 3, which is our rapid repolarization. Okay, so let's see what's happening in each of these phases. So at phase 4, we're at rest. And so what we have is an increased permeability to potassium. Again, that large P just means the permeability, okay? We have a decreased permeability to sodium and a decreased permeability to calcium, okay? And we already know this. We know that this is how a cell starts at rest, be it a neuron, a pacemaker cell, or a contractile cell. We start with more potassium doors open, so that's an increased permeability to potassium than what we see for sodium and calcium, okay? Now, the first part of this is that we rapidly depolarize the membrane. So we increase the permeability to sodium. Okay, and that's simply because we open sodium channels. Okay, very simple. So the depolarizing phase here is very simple. From rest, straight away we open one channel. It's a sodium channel. Sodium rushes in, and we depolarize this in one go. Okay. The second phase, let's label that out here. Oops. So I'll put it here. This is phase 0. All right. The second part of this is phase 1. And what happens here is just the opposite of phase 0. So we close that sodium channel. And so simply we decrease our permeability to sodium. Okay. Right. I missed one of these. There we go. Now, phase 2, which is also called the plateau phase, right? The plateau phase. Here, what we do is we open up our calcium channels and close our sodium channels, okay? So closing sodium channels is important because it's going to prevent, closing potassium channels. So we had potassium channels open here. So we're going to close those potassium channels. And open calcium channels. Okay, this is getting a bit jumpy. All right, and so what we have here now is an increase in the permeability to calcium and a decrease in the permeability to potassium, okay? And this is really important. This helps to delay the action potential. We have two really important functions for calcium, okay? Calcium is not only helping to sustain the action potential, but it is really important in the actual cross-bridge cycling here. So in a contractile cell, remember this is different from a pacemaker cell. In this cell, we actually have actin, myosin, we have the sarcomere, we have that cross-bridge machinery, and so we need to delay this so that we can have some time for calcium to get into the cell. Okay, that excitation, contraction, coupling. I'll talk about that in a minute, but that is why we have the plateau phase. So this is really just an interrupting in the repolarizing process in order to allow some time for calcium to get into the cell, interact with troponin, slide tropomyosin out of the way, all of that stuff that we talked about with skeletal muscle, that also takes place here because we also have the sarcomere and cross-bridge cycling happening, okay? So that is the function of the plateau phase. We sort of interrupt the repolarizing by shutting those potassium channels really quickly. We open up calcium channels, which is going to help get calcium into the cell. Remember, we said that the source for calcium in cardiac and smooth muscle is not only from the SR, but outside of the cell. And this is how it gets into the cell. We have to leave a period of opening those channels so that calcium can actually get in. Okay, now the final phase here, phase 3, is we just flip-flop what's happening here. So we close those, I'll bring it down here. We close those calcium channels and we open our potassium channels. All right, and as a result, we increase the membrane permeability to potassium. That's going to help us rapidly repolarize. And then we shut those calcium channels, hence decreasing our permeability to calcium. Okay? All right, and we get right back down to rest, which is again, phase 4. Okay, so I'll go over this again, just so that we can understand a little bit better. We start at phase 4 at rest. We know at rest that we have more permeability to potassium because we have more potassium channels open. So we have an increased permeability for potassium, a decreased permeability for sodium and calcium, okay? Now we rapidly depolarize here by opening up one channel. We open up a sodium channel, sodium does its thing. We know that its ECDF is strongly into the cell, right? It's gonna rush into the cell. That's gonna be the upstroke, i.e. our action potential. Right? Now, immediately after we depolarize, here we're going to try to repolarize. So we begin repolarizing by simply closing that sodium channel, but then we have to sort of interrupt this repolarizing phase with phase 2, and that plateau phase is sort of stalling to allow calcium to enter the cell. So here we close that potassium channel to sort of stop the repolarizing, open up a calcium channel to get calcium in, and then in phase 3, we can flip that and continue with the repolarizing process by opening up potassium channels and closing those calcium channels, okay? Any questions on this bit? So it's really important to understand how the pacemaker cell differs from the, right, how this differs from this. I can't get these both in. But we can see here that the upstroke, the action potential happens by the movement of two different ions, okay? In the pacemaker cell, the depolarizing happens by the movement of calcium through those slow calcium channels, okay? In our contractile cell, the depolarizing happens by the movement of sodium, right? So make sure you're making those distinctions, make sure you're making those notes. Also, here in the contractile cell, we have that contractile machinery. We don't have that here in the pacemaker cell.